All right, welcome to the day 8 video. You can pause to check your homework answers. Homework over break, you've got one question from the textbook and then packet page 5. So go ahead, pause your answers, and like normal, I will pause on each of the worked out solutions. So in these ones here, we had squares and then we had rectangles of height and with height of 1. So you had your line minus your parabola to give you the length of a side of the square, and then side times side then gave you the area of the square, and then the dx is the little bit of thickness. So in B, the one side of the rectangle is again line minus parabola, because top minus bottom, and then the height was just 1. So when you got y by itself, you had y equals square root of 4 minus x squared. Well, that's just this length here. So for the square, if we're doing like a top view, that's the square and it's coming out at us. So really, it needed to be twice the length of y for the side in the square. And then side times side, so that's why the whole thing is squared. When you have an equilateral triangle, if this is A, then this is 1/2 A. That's across from the 30. Here's the 60. So across from 60 should be square root of 3 times what's across from 30. So you have square root of 3 over 2A. So the A was this same length that the side of the square was in part A. So you had square root of 3 over 2 times that A, plus the A itself. So this is essentially our height. This was our base, and then times the 1/2 for the triangle. Now in C, you had 1/2 pi times radius squared. So because it's the radius and only goes halfway across, that's why we didn't have the 2 out in front like we had in the others. And the last one, here's your isosceles right triangle. Well, normally we had like a squared of 2, but if you divide everything by square root of 2, then that makes the a be the hypotenuse, because we already knew what the hypotenuse was based on the other ones. And then the legs are both just that value of a times square root of 2 over 2. So there's that value of a. So here's 1/2 your base and your height, or you could have just said that squared, because the base and the height are the same in your right triangle. So for this one, we were going just from 0 to 1, and we wanted to go around the y-axis. So for shells, stuff like that's your typical rectangle. Your height is just the function itself, and your radius is like that little bit there, so x for the radius. You had to use a u substitution. You had to correct by -1, and then the antiderivative wasn't too bad from there. All right, so today is more practice, like you saw in the homework, because this is a challenging topic, but it is a very common topic on the AP. So before we get to the notes, you'll need for the homework the area of an ellipse. So you'll want to write this down somewhere. So if you have an ellipse where we're calling one of the radii B and the other radii A, the area of our ellipse we would say is pi AB. So kind of like if you have pi r squared for a circle, it's r in both the up direction and the right direction. Well, these ones are different. That's why it's pi AB. All right, so we've got a region. We've got y squared minus 2y. That's that parabola opening to the right. We've got x equals 3y. That's the line there. And we're going to have cross sections that are cut perpendicular to the y-axis. So it's basically that rectangle there. And they're going to start out, they're going to be semicircles. Well, your basic setup for a semicircle is you have 1/2 pi times some radius squared. The way our slices are, we're hitting the y-axis, so we should be dy. Let's figure out our bounds by setting those equal to each other. Y squared minus 2y is equal to 3y. That's y squared minus 5y equals 0. And if you pull the y out, you get y minus 5 equals 0. So we'll get 0 and we'll get 5 for our bounds. So our semicircle, like three-dimensionally, is kind of coming off like that. So our radius would be half of whatever that length is. Well, the length that we have there, we would want to do a right minus left. So we're going to do line minus the parabola. So if we distribute that and neaten up, we're going to get minus y squared, and then we'll get plus 5y. But that's all the way across, so we've got to take half of that for our radius. So we're going to have minus 1/2 y squared plus 5/2 y. We can pull the 1/2 pi out front. And if we multiply that out, we're going to get a 1/4 y to the 4th. The negative 1/2 times the 5/2 will give us negative 5/4. So we'll have two of those, so we'll have negative 10/4 y to the 3rd. And then we'll have plus 25/4 y squared. So we'll take our antiderivative. We're going to have y to the 5th, so now we'll have 1/20th out front. We'll have y to the 4th, so we're going to have negative 10/16, which reduces to negative 5/8. And we'll have y cubed, so out front we'll have 25/12. And we're going to evaluate that from 0 to 5. Now on your test, remember at this point you could sub in your calculator. The 0 is not going to do anything, but if you sub the 5 in and then multiply by the 1/2 pi, I'm assuming everyone could sub that in okay, we would get 625 pi over 48. So in the next one, we're going to do the same region, but this time we've got isosceles triangles that are resting on their hypotenuse. Well, our basic special right triangle, AA and A square root of 2. But we want to have, because it's resting on the hypotenuse, let's make it so that hypotenuse is just A. So we'd want to divide everything by square root of 2, and we'd get 1 over square root of 2, or in other words, square root of 2 over 2 for each of these. And now this is just A. So our area formula for that right triangle, we saw this in the homework, will just be square root of 2 over 2A times square root of 2 over 2A times 1/2. And we've just got to figure out what A is. Well, A is this entire length here. It's just the right minus the left. Well, if we go back to the last problem, the neatened up version of the right minus the left was this right here, the minus y squared plus 5y. Because we don't need to half it because it's not a radius, it's going all the way across. So in our integral, we're going to be from 0 to 5 again because our bounds are the same. We have 1/2 because of the area of the triangle formula. And then base times height, they are both going to be square root of 2 over 2 times what our A was. And the A was the minus y squared plus 5y. And then that is all squared because the base and the height are the same. Well, if we square root of 2 over 2, that'll give us 2/4, which is 1/2. Times the 1/2 that was already out front will give us 1/4. And then we'll just have to square out the minus y squared plus 5y. All squared. So that'll be 1/4. Oh, I don't know why I switched this to 4. That's a 5 there. 1/4 times, maybe we should FOIL it out first. The integral from 0 to 5, we'll have y to the 4th minus 10y cubed plus 25y squared dy. And that would be 1/4. And you notice there's lots of similarities to the last one. We'll have 1 over 20 y to the 5th. We'll have 10/4, which is 5/2 y to the 4th with a minus in front of it. And we'll have 25/3 y cubed, evaluated from 0 to 5. This is where you can sub it in the calculator on the test. So we'll just get 625 over 24. Now let's show you two ways you can think of that right triangle thing that we just did. First, we'll show you the way that we did it again. Okay, and let's, instead of A, let's call this H, because H is the hypotenuse. So we found that eventually, so we originally could call this, we originally called that H and H square root of 2. Well, if we divided them all by square root of 2, we found that these were square root of 2 over 2. And now this one was just H. Okay, so that's one way to think about it. But you could also do base times height by drawing in a perpendicular here. Because this is an isosceles right triangle, that would make this one be 1/2 H. Well, this is 45, 45, 90 here, so that would make this also be 1/2 H. Well, let's look at our two area formulas here. This one would be the entire base of H times our height of 1/2 H, and then the 1/2 that's in the area of the triangle formula. So this would give us 1/4 H squared, where H is the hypotenuse. Well, let's look at this one here, where if we do area of a triangle using our two legs. So area would equal 1/2 that's in the area of the triangle formula, square root of 2 over 2 times H for one of the legs, square root of 2 over 2 times H for the other leg. Well, square root of 2 over 2 times square root of 2 over 2 gives you 2 over 4, which is 1/2, times the other half, which is a 4th, and H times H is H squared. So notice in both cases, however you decide to think of it for doing the area of that triangle, you get 1/4 the hypotenuse squared. And in the cases we've seen so far, the hypotenuse is what it's sitting on. So that hypotenuse is really either a right minus a left or a top minus a bottom in terms of our area that's bounded by the functions. So we're going to go back to that same picture. And we're going to do rectangles where the base is twice the height. Well, for our three-dimensional picture here, this part's the dy. We can take from the previous problems that are right minus left simplified to minus y squared 5y. And if the twice as high as they are wide, we've just got to double that. So we'll have minus 2y squared minus 5y for the height. So our integral will add up the volumes of all those slices. So the base times the height is just minus y squared minus 5y times minus 2y squared minus, wait a second, that should be minus 10y. Sorry about that. When we double that, that should be minus 10y. And then dy, and we're still going from 0 to 5. So if we multiply this out now, we're going to get a positive 2y to the fourth. Our outers and inners, we're going to get a positive 10y cubed, another positive 10. So this is a three-dimensional shape on the right of those rectangles. This here is our dy. That's a little bit of thickness. That's like that dimension. The pink parts match up, and we can use from what we saw in the previous problems. That's negative y squared plus 5y. And they said they're twice as high, so we'll double those. We'll get negative 2y squared plus 10y. Well, our integral is still going from 0 to 5. We'll just have the base times the height times dy. We can FOIL that out and get a positive 2y to the fourth. We'll have a negative 10y on the outsides, negative 10y on the insides, so we'll have negative 20y cubed. And then we'll have a plus 50y squared. Do your antiderivative. We're going to have 2/5 y to the fifth. New exponent is y to the fourth. Divide out front by 4, so we'll have negative 5y to the fourth plus 50 thirds y cubed. And we're evaluating from 0 to 5. And from there, we could put it in our calculator. We get 625 over 3. Now, remember, if it gives you a decimal and you want it as the exact value, you can go to menu number, approximate fraction. Or remember, the AP rounding standard is out to 3 places. All right, so a new one now. So we've got the graph of sine x there, kind of roughly drawn, and then we have y equals square root of 2 over 2. And we're going to take cross sections that are perpendicular to the x-axis, and we want them to be squares. Well, square is side times side, so whatever this is, we're just going to have that squared for our square. Well, it's top minus bottom because we're in terms of dx. So our top is sine x, the bottom is square root of 2 over 2. So we're just going to have sine x minus square root of 2 over 2. And again, that's squared is coming from we're doing side times side for the square. Now, the tricky thing might be setting those equal to find what our values of x are. Well, sine is equal to square root of 2 over 2, or in other words, 1 over square root of 2 before it was rationalized, when our reference angle is 45. And it could be positive square root of 2 over 2 in our first or second quadrants. So 45 reference in the first quadrant is 45, second quadrant would be 135. We got to convert those to radians, and we would get pi over 4 and 3 pi over 4. And for this one, if we were to FOIL it out, we would get a sine squared x, which at this point we don't know how to handle. Okay, we are going to learn how to handle that algebraically, but right now we don't know how to handle that. So the best we could do right now is punch this in the calculator, and to the nearest thousandth, we would get 0.071. Same region now, but this time we're going to spin it around x equals pi. Well, x equals pi should be right here, because that's where sine should hit the x-axis. So when you're spinning it around something, that's where you have disks, washers, or shells. If you're just doing cross sections, it's just the area of the cross section times either dx or dy. So two different ways that you could be finding a volume of a solid. So because there's some gap there, we've got to use either washers or shells. But if we tried to use washers, the inner edge and the outer edge are the same function. So if we set that up, it would just end up giving us 0 there, which wouldn't make sense. So this means we have to do shells. So an example of one of our rectangles would look something like that. Our height of that, because we've got 2 pi integral some radius times some height, and we should mention that we're dx because that rectangle would be slicing vertically. And because it's dx and we know from the last one, we can fill in our pi over 4 and 3 pi over 4 as well if we want. But anyway, our height is just a top minus a bottom. So that's just our sine x minus square root of 2 over 2 that we saw from the last problem. The radius is that length there. Well, if we do a right minus a left, it's got to start with the pi. And the part we're subtracting off, this, is just x here. Because our basic definitions, x is coming out to the right, y is coming up. So the thing that we're chopping off is whatever the x value is. So we'll have pi minus x. So for example, if we're doing our rectangle at x equals 2, we would do pi minus 2 to get that this is like 1.14 and change. So this one, if we multiplied out, we'd get an x sine x, and we also don't know how to handle that yet. So best we can do is put this in the calculator, and we get 2.995. All right, we'll finish with two true-false questions. So if f of x is continuous and decreasing for all values of x, and we know that f of 1 is greater than 0. So we know there is a point that's above the x-axis, and it's always decreasing. Then the function has to have one root. Well, what we want to think about is if it's always decreasing, does it have to decrease in a way that it passes through the axis? And it doesn't necessarily have to. Think of something like a exponential decay function. So this one would be false, because you could have f of x equaling like e to the negative x, because that would show exponential decay. You could have 1/2 raised to the x. That's also another exponential decay one. So our last one, if f of x and g of x are continuous, and they're also monotonic. So that means they are always increasing or always decreasing. Okay, or they can be constant, because it doesn't say strictly increasing or decreasing. Monotonic means that they could be constant or increasing or constant or decreasing. So we want to know when you add them together, does it also have to be monotonic? Does it also have to increase or decrease? Well, an example would be if we let f of x equal sine x plus x. Basically what that looks like is imagine like y equals x, and sine's going to kind of follow that. So that is strictly increasing. Think of g of x as negative x. Well, that's just a linear with a negative slope. That's definitely always decreasing. Well, when you add those together, that's going to give you sine x, which sine x both increases and decreases, so that is not monotonic. So that's a counterexample of how this one could be false. All right, that's it for day 8. So you got day 8 homework that will be due after break. Enjoy your break, take some time to rest, and we'll see you in the new year.